Welcome to this lesson on dynamic data structures. Throughout this course, you've used arrays to store multiple values of the same type, or you've used arrays to store even structures. The problem with arrays is we need to know our array size when we compile our program. And a lot of times we won't know the size of the data that we need to store. And the solution to that is to allocate memory dynamically as your program's needed, and then give back memory when you no longer need it. And in this lesson, we're going to learn how to do that. We'll also learn how to create common dynamic data structures, such as a singly linked list or a doubly linked list, or a binary tree. So let's go ahead and get started. There's two primary routines that you'll see in C programs for allocating memory dynamically. The first is malloc, M-A-L-L-O-C, for memory allocation, and the second is calloc. In this program, we're going to use malloc to allocate memory for us dynamically. When we allocate memory dynamically, we specify the number of bytes that we want. And then we get a pointer back to that memory location if malloc was successful. If malloc is unable to allocate the memory, it will return null. So we can test the return result to see whether or not we're successful or we need to display an error message because the memory couldn't be allocated. So in this program, we're going to allocate memory for a character string, an array of integers, and an array of floating point values. And so we start off by including standard lib.h, and then we declare our pointer variables, a pointer to a character string, a pointer to integer values, and a pointer to floating point values. We then use malloc to allocate 512 bytes. And we assign the result to the string pointer. And if it's successful, meaning it doesn't return null, we display the message successfully allocated a 512 byte string. And then we actually use the string. In this case, we're going to loop through the letters of the alphabet, assigning it to the new string array. When we get to the last letter of the alphabet, we're going to append the null character and then display the corresponding string. And so we've allocated memory, assigned values to it, and then used it. And when we're done with it, we should release some memory back so it can be used for other purposes by calling the free function. After we allocate our string, we're going to do something similar to allocate an array of integers. And in this case, we're going to tell malloc we want 1,000 bytes, or no, we want 1,000 of the size of int. So it's going to calculate the number of bytes in int multiplied by 1,000 and do the allocation. If it's successful, it will return a pointer to the memory location. If an error occurs, it will return null. And in this case, we're just simply going to display a message, hey, we allocated a 1,000 byte array, or 1,000 integer value array, and then we're going to release the memory. And then we're going to try the same thing for an array of 25 floating point variables. Again, follow the same process. Tell malloc the number of bytes we need, and then test to see if it was successful by testing whether or not the pointer is null or points to a memory location. And again, if it's successful, we're just going to display a message saying that we allocated it, and then we're going to free the memory. So let's go ahead and run this program. And so in this case, we successfully allocated a 512 byte string. We then assigned the letters of the alphabet to it and displayed it using printf. And then the program tells us that we successfully allocated a 1,000 element array of type int and a 25 element array of type float. And we could have assigned values to those memory locations too, using either a pointer or an array structure. So your programs, when they use dynamic memory, should allocate the memory, use the memory, and then when they're done, release the memory back using the free method. And so this function does just that. It creates a character pointer, and then it's going to allocate a 512 element character array. And if it is successful, it will then assign the letters of the alphabet to it, print it, and then free it. And so there's times when you'll hear terms like memory leaks and things. And those typically happen when a program allocates memory and then fails to give it back. And so the memory somehow gets kind of lost, or our memory gets smaller and smaller and smaller because it's kind of leaking away. And so in this case, the program is very similar to the one we just ran. We allocate our memory, use it, and then free it. Newer C programs will normally use the calloc routine to allocate memory dynamically. And in this case, we're going to do similar processing. We're going to allocate a 512 element character string, a 1000 element integer array, and then a 25 element floating point array. And we're going to use it using calloc. And calloc's normally what you're going to see in most newer programs. And so again, it's going to return the null value if an error occurs and it can't allocate to memory. Otherwise, it will return a pointer. And so when we run this program, we see that calloc successfully allocated to memory. And then at the bottom of the program, you can see that after we allocated it, we freed it back for use. So the ability to allocate memory dynamically gives us the ability to create some interesting data structures. And the first is called a singly linked list. And so we've got a list of values. In this case, we've got something that points to the first element in the list that we call start. It's just a variable. And then we have a list that the first element is 1, the second element is 2, the third element is 3. You can see that we've only got 3 data values in our list, so the third element, rather than pointing to the next element, points to the null. That's how we know where our list ends. Now, if we want to add more elements to our list, we just allocate memory for them and update our pointers to build the list. And so let's look at a program that does just that. To start, we define a structure named node that's going to have a value, and it's going to have a pointer to another structure named of type node that we call next. And so if you look at our linked list, each one of them has a value and then has a pointer to the next one in the list. So 1 points to 2, 2 points to 3, 3 says I've got none left, I'm going to be null. We have a variable called start that always keeps track of where our list begins. And so you can see in our program, we define a node to look very much like that. Hold a data value and hold a pointer. Within main, we're going to allocate memory to store our variable start. And so we use calloc in this case, and we just allocate memory. And so start is a pointer to the first node in our list. Since we have no values in our list, we say start.next, or start the next member is equal to null. Now we're using pointers to structures, and you'll recall from our previous lessons that when we do, we use the arrow notation to get to our members. And so we're also defining a variable called current node, and we're assigning it the value start. After that, we're doing a for loop that loops from I equals 1 to 10 to get the values 1 through 9 into our list. And you can see within our loop, we say current node.next, and current node was currently the start. So we're going to allocate memory for our new node. We're going to point that memory to from the member current node.next, so it's got the pointer to the new memory. We're going to say current node equals current node.next, and for that current node we're going to assign its next pointer null. We've not added anything else to the list yet, and we assign it the value I. So after our first iteration, we have the start variable that points to the start of our list. Our first node in the list contains the value 1, and it points to the null because there's no other nodes in the list. We then come for iteration 2, allocate memory for a new node, assign current node.next to point to it, and then update its current node.next to be null, and assign it the value 2. And so we build our linked list in this way. Once we've done that, we can come back and we can see current node.next is equal to start.next. Start.next is the first element in our list. And as long as we're not pointing to null, we're going to display that element's value and then update current node to be current node.next. So we'll move along to the next node and we'll say, is it null? No. Display its value. Move along to the next node. So we can walk through our singly linked list in this way. When we run our program, Sure enough, we see our values 1 through 9, which have been assigned to the list. So often as we're building lists, we may want to keep the list in order, or we may want to have some other processing, so we're inserting them by date, or we're inserting them alphabetically, something. So in this case, let's assume that we had our list of 1 through 10 values, and the 10th one points to null, there's not one after that. And we want to insert the value 500 after the value 5 in our list. And so to do that, we're going to move through our list, beginning with start. We'll go to the first one, say, is it the value 5? Nope. Move to the next one. Is it the value 5? Nope. Move to the next one. Eventually, we'll get to the value, or the node that contains the value 5. At that point in time, we'll allocate memory to store the value 500, and we'll have the current node's next item point to that new memory. Then we need to tell 500 that it needs to point to node 6. And so we'll see as we traverse our next program how we'd insert an item into a singly linked list. So we start out, we define our node, and then we go through and build our list with the values 1 through 9. And then after that, we want to insert the value 500 after the node with the value 5. So we need to go find the node that has the value 5. And so we assign our current node to be start.next, the first node in our list. And while the current value is not equal to 5, we're going to just loop through nodes. Are you 5? Nope. Are you 5? Nope. Are you 5? Nope. When we find the value 5, we then allocate memory for a new node. It's going to be the one that stores the value 500. And we say new node.next is equal to current node.next. That's how we get the new node to point to the node that has the value 6 in it. We then assign the value 500 to the node, and we say that our current node.next, we're currently at the node that has the value 5, is equal to the new node. So we've successfully inserted it. And so then we can go back to the start of our list and loop through it, and we should see our new value. So when we run this program, sure enough, we see 1, 2, 3, 4, 5, our newly inserted 500, and the rest of the list. Just as there's times when we want to insert items into a singly linked list, there'll also be times when we want to delete an item. And so in this case, we're going to delete the node that has the value 5. So our program starts and we build our linked list. We're going to give it the values 1 through 9, as we did in the previous. Now we want to delete the node that has the value 5. So we start at the beginning of our list and we start searching, is this the node with the value 5? But in this case, we're going to use two nodes. One, we've declared a node or a variable that's called previous node. And so it's going to stay one node back as we're moving through our linked list. And so while it's in the loop, the previous node is going to point to first start, and then 1 as we're pointing to 2. It will point to 2 as we point to 3. It will point to 3 as current node points to 4. It will point to 4 as current node points to 5. So when we find our element in the list, previous node is one node back, and we'll use that then to easily delete our item. So to do so, we just say previous node.next is equal current node.next. And by doing that, we've updated our list so that the node with the value 4 now points to the node with the value 6. And we can free the current node that has the value 5, and our item's gone from our list. And we can now go back to the start of our list and traverse through our list displaying the values. And we should see that the item 5 is gone. And sure enough, we get 1, 2, 3, 4, 6, 7, 8, 9. So we've successfully deleted the item from our list. To simplify the process of inserting and deleting items from a list, many programmers will use a doubly linked list. And you can think of a doubly linked list as having pointers forward and pointers backwards to the next and the previous nodes. So in this case, we say that start.previous is null because there's nothing before start. And 1 points to 2 and 2 points to 3, and 3 doesn't have anything after it, so it points to null. 3 points back to 2, 2 points back to 1 and 1 points back to start. And with these forward and backward pointers, it makes it very easy to insert or delete an item in the doubly linked list. So let's see how things have changed. To start, our node now has a field for our value, has a next field because it's pointing to the next node in the list, and it has a previous field that's going to point to the previous node in the list. When we start, we allocate a node for start, and we assign its next to null, and we assign its previous to null. It's the only node in the list. And then we make current node equal to start. Now we're going to loop from 1 to 10, putting the values 1 through 9 in our list. And to do so, we allocate memory, and we point it at current node.next. And then we say that the current node.next, so that thing we just created, its previous link should point at the current node. And so we created a new link. It wasn't, its previous and next weren't pointing anywhere yet, so we said, go to the current node, look at its current next field, that points to the new one, make that one's previous field point back at me. Then we say current node equals current node.next, and current node.next equals null. So we created the node for value 1, and we've assigned its next field null because there's not a value 2 yet, and we've made its previous field point back to start. We then iterate again. I guess we assigned a value 1 to it. We iterate again, and now we're going to allocate memory for node 2. We're going to have its previous node point back to node 1, its next node point to null because there's not a next node yet, and then we'll make our current node.next point to 2, and then we'll assign the value. And we'll repeat this process to build a loop. And so we've got our values 1 through 9 in our loop, and now we want to insert the value 500 after the node with the value 5. And so we can go through our loop, and in this case we don't have to worry about anything previous because we've got a doubly linked list, and so we find a node that has the value 5. We then allocate memory for a new node, and we say new node.next equals current node.next because we're inserting it. And then we say new node.previous equals the current node. We assign its value, and we have current node.next point to the new node. At that point in time, we've done our insertion, and we can go back and loop through our values, and we should see that the value 500 has been inserted. And sure enough, it has. And so just as there are times when we want to insert a node into a doubly linked list, there will also be times when we want to delete a node from a doubly linked list. So this program starts out and it builds our doubly linked list just like before. We then want to delete the node with the value 5. So we loop through our list until we find that node. So after we've found it, the current node should be the one pointing to 5, but if it's null, or if its pointer would be pointing to null, it would mean that was the last node in the list, and we need to do a little slightly different processing. And if its previous was null, that means it was the first node in the list, and we need to do a little extra processing. And so once we've updated its previous and next nodes, we can free the current node, and we'll go back to the start of our list and loop through, and we should see that the node with the value 5 has been deleted. And sure enough, our list goes 1, 2, 3, 4, 6, 7, 8, 9, and the node's gone. Now, a binary tree is a dynamic data structure so named because each node can have 2 branches from it. And the way that we construct a binary tree is we get a value, so let's say 3 is our first value, and we create a node for it. We then get our second value, it could be 1, and we look at the value 3, and if the new value 1 is less than 3, we start searching down the left side of the branches for a location to put it. And so we'll put the value 1 into our tree. If the next value we get is 4, 4 is greater than 3, so we're going to go off to the right, create a node for it, and put it in. Let's assume the next value is 2. We're going to start at 3. 2 is less than 3, so we're going to go left. We're going to compare 2 to 1. 2 is greater than 1, so we're going to go to the right and put the node. And then finally, if we get the value 5, we're going to start at 3. 5 is greater, so we go right. We'll compare it to 4. 5 is greater, so we're going to go right, and we're going to create a new node. And so a binary tree is typically defined in a recursive fashion, and it makes a process of adding a node to the tree, deleting a node from the tree, and actually traversing the tree to display values in sorted order pretty easy. So let's take a look at our code that does just that. Our node structure has a value field that we're going to store the node's value in. It has a pointer to its right branch and a pointer to its left branch. We then have a function that we're going to use that's going to insert a node into the tree. And so to insert the node in the tree, it has to find the correct location to put the node. And the way that it does that is it's going to allocate space for the node, and then it's going to look at the current node that was passed to it, and if the value is less, it's going to insert the value on the left-hand side of the tree, and if the value is greater, it's going to insert the value on the right-hand side of the tree. So you see, it does an insertion by calling itself. It's a recursive function. And you'll want to spend a little bit of time with a pencil and a paper adding nodes to the tree and drawing where they end up. But it turns out that this allows us to build our tree in the manner that we just kind of discussed. To display the tree's contents, we'll be passed a node, and if the node's not null, then we're going to display its left branch first, come back, display our value, and then display its right branch. Because our left branch are values that are less than us, then we have our value, and our right branch are values that are greater than us. So this allows us to display our tree in sorted order. Within main, we just simply create a variable, a pointer that's called root, and we assign it null because we don't have anything in the tree yet. And then we can insert a value by passing the root to the tree so it knows to start at the top of the tree and start looking through the branches as to where to put these. And sure enough, the values are similar to how we constructed our previous tree. And so let's go ahead and run this, and we should see our values in sorted order. And sure enough, it displays them 1, 2, 3, 4, 5 in sorted order. And so both our insert tree function and display tree function are recursive functions in that they're recursively calling themselves each time they get a node. They're looking at the left branches, looking at the right branches. The insert's deciding, where should I put this value? Is it bigger than me? Then it's going to go right. If it's smaller than me, it's going to go left. And then display tree will just keep looping or start at the root, and it will try to move left as far as it can. And then we'll display a value, move back up a level, display that value. If that value has a right branch, it will display those. So congratulations on learning C programming. I always say that learning your first language is a time-consuming task. Learning your second language takes half that amount of time, and learning your third language takes half of that. You now have a great foundation to learn and, more importantly, appreciate C++ programming. C++ is very much like C. You have the same loops, the same ifs, the same variable types, but you'll have greater functionality. C++ supports object-oriented programming. So I recommend that you should take my C++ course, possibly followed by my C# course. And then good luck with your programming endeavors.